Welcome to Season 6 of the Prosthetics and Orthotics Podcast. We are absolutely thrilled to have you on board. We're talking to experts who know their stuff, the patients who've experienced these technologies firsthand, the vendors who provided the tools, and the thought leaders shaping the future. Together, we will uncover the ways to make the lives of those relying on these incredible technologies even better. We hope these discussions are going to be the highlight of your day.
Hi, everyone. This is another episode of the Prosthetics and Orthotics Podcast with me, Joris, and always with Brent Wright. How you doing, Brent?
Hey, Joris. Doing well. This is going to be a fun episode. We do not have a guest today, and for those that are listening, we do this every now and then. And Joris, I was actually talking to some people, and they seek out the episodes that we don't have a guest sometimes because they feel like the insight that they get between two and the banter and all that stuff that goes back and forth is very valuable. And so I think that's why it's important to keep on doing these.
Sure, totally. I think that's great. I like talking with you anyway. That's how this got started in the first place. So let's just continue doing it. Let's just keep doing it. So what are we talking about today?
Well, it's something that we haven't talked a lot about, and that's metal 3D printing. And I'm going to be like you with prosthetics, right? I do not know anything about metals other than it's super cool, and it seems to be very expensive. But I'd love for you to maybe share some insights on that, and then we can go back and forth on, hey, these are some things that may be useful in the prosthetic industry. Does it actually make sense at any time? Or if nothing else, we get educated about what metals can do.
Okay, cool. Yeah, definitely. So a little bit of overview first is a couple of metal 3D printing processes. Some of them are indirect and some of them are direct. We'll talk about the most relevant ones. Like one of the ones that's very relevant, very cheap actually, is to use vat polymerization. So that's like your Formlabs printer or your Frozen printer, these kind of the resin-based printers. And what you can do is you can actually cast from these lost wax cast, or you can actually chrome as well, these kind of plastic models. And they're very fine models. Environmentally and people safety-wise, it's not amazing. You should be very careful while doing this. But you can get very finely designed objects. If you want something ornamental, I can imagine like a toe cap, like a thumb type thing, small kind of tool like things you could do with this technology as well. Then also with vat polymerization, which again is a vat, right? With a photopolymer resin in it that gets hard when it comes into contact with light. So the laser, usually by a galvanometer, laser essentially draws a light in that vat. That thing is then taken out. The hardened object has to be cleaned, usually with IPA or another kind of substance, and then it gets cured. It usually cures by itself just in the light, but it'll get fully cured usually in kind of an oven. And some of these materials, like carbon, you maybe have heard of. Those are guys doing the Adidas shoes. They're doing like a dual cure kind of resin where they put it in an oven as well. So for these kind of processes, you can get these really fine objects. Now, another version of this is slurry SLA. And that's a process like, for example, Hollow AM has it. And a couple of other companies have it as well. And this has it's actually this is good for really fine objects, really small objects. And essentially what happens is after the object is printed, it kind of has a suspension of metal in it. And then it's sintered after the fact, just normally like you would with a sintering process. And then you can end up like really tiny metal parts. Now, this is not as accessible. You need to do this in an industrial thing. You need to buy a unit. You can buy a Hammer Lab, which is kind of a cheaper version of these printer from one of the vendors. But this is very nascent as a technology. But this is something for like, smalling, tooling kind of things. If you wanted to make a fastener or a screw that like no one else can make in the world, this would be really good. The micro level kind of things like millimeters to a half centimeter kind of thing. Then we have binder jet. So binder jet there's a lot of hype about binder jet at the moment. Essentially, it's like inkjet, like you have your printer at home, but it then puts a binder material on metal powder. That material is then the object is taken once all the layers have been processed. The object is gingerly taken out in its green state, and then it's debound and sintered. There's shrinkage, and that shrinkage changes depending on the wall thickness and the size of your object and the shape of your object, lots of stuff. So binder jet is a really great technology. If you were like, for example, you wanted to make 100 parts and you want to keep making them, and you wanted to do like your hanger or something, you wanted to make spare parts all across America, right? Then you could take the investment in qualifying these 100 parts, which would mean you'd have to print them out again and again and again to see the right shrinkage rates, right? And then once you have that, you can have a library of spare parts and print them out like on a lot of different places at once. And it'd be super cheap, right? This uses MIM powder. And MIM is a really process that a ton of stuff is made from. And MIM powder is super cheap compared to the other stuff we'll get to in a bit. So binder jet is cool, but if like, for example, if you had like a service bureau, or you can get different files every day with different geometries, it'd be a total nightmare. It wouldn't work. So that's kind of like the limitations there. It's good for fine objects. Think of like millimeters to several centimeters range. And there's a limitation here is in the green state. So if the object is like a wine glass kind of shape, right, then in the green state, it's going to collapse because it's too fragile. It's the same problem that we have in the previous thing, the slurry SLA as well. It's geometry dependent on what you can do. And you need that sintering step where you're essentially putting it in an oven and hardening it, getting rid of all the other material and space in it. That is just, a really difficult to understand step. So don't do that. I wouldn't do that for prototyping or inventing things or as a service or something like that. But hey, this library of spare parts all over the world, that could be a doable thing for binder jet. Super low cost parts. We have some other processes, but that's not really important, but they're kind of similar. Then there's also one that's bound metal. Now, bound metal is very analogous to the binder jet process, where you've got a filament printer that has metal parts inside of it. Desktop Metal has one of these. Markforged has these printers as well, and these are quite accessible. But you could also do it on your Ultimaker or even like your Prusa clone printer. And so the printing itself you could do in the office. The problem is you need to debind it and then sinter it. And there's no real ovens available. Like you need to buy like an industrial oven. And there's no real ovens and debinding equipment. That's also very finicky and health problematic. So the actual printing process is super cheap. This is a really, really cheap process to do. But the sintering debinding, you'd have to have a partner for that. I would not advise you doing that yourself. And also there needs to have a little bit more of a supply chain. There needs to be kind of like a little bit more of a understanding around that. There's not that many products coming out. There are some now that are going to be available. Markforged, for example, will sell you the whole setup. And if you're like a metal shop, I would think, okay, attempt that. But if you're doing like a carpet floor type of thing, I wouldn't do this in a carpet floor type environment, kind of like. But super accessible. We're talking parts like a several dollar parts, that kind of thing. So that's really nice. Then we've got DED. There's a couple of other processes that use DED kind of process. DED just means directed energy deposition. It could use a wire. There's WAM and all this. The one that would be kind of relevant to us is like a Meltio-like DED. So a laser or a bunch of lasers will melt a wire. Now, because it uses wire, the welding wire you could use at home or whatever, or use at construction sites, that's super cheap stuff. DED makes near net shaped parts. So you're going to end up with something that's really rough, right? A really rough looking and kind of artisanal kind of looking. So, but if you're okay and you design that and you're okay with showing these metal layers and looking kind of weird, it's super cheap. You can make like a leg brace type part for like $20, right? Now, the problem is, of course, the machining, right? So afterwards, if you would say, no, it needs to be smooth, then you're going to machine it. Maybe that'll even be more costly than this process. So DED processes they work really well for certain processes. And you can also use them to repair parts and put different dissimilar metals on top of each other. The reason I'm including them is that if you wanted like brace type things and stuff like that, it could be really interesting. But you're going to have to do some machining. These machines are some of them are quite affordable, $100,000 or something like that. Compared to, by the way, the binder jet machines, which will be start at like 50, but most of them will be up near 100,000 or something, or even like 800K or something like that. The bound metal machines could be any printer really, but if you want to get into something that'll do it really well, it's like a 20, 50K usually, and then with the rest of the setup, right? And then usually you're looking at like 200K or something like that. And then on top of that, what do we do? The slurry SLA is usually like there are some machines that you could find. They're usually lab-based machines, but really you'd want to get to a vendor for that. Now, then we have powder bed fusion. Powder bed fusion is the most prevalent metal printing technology. It has really highly accurate objects that require quite a lot of machining, and it's pretty tough to get your part right the first time. So, often maybe the first 3 or 4 parts will fail. So again, from a service perspective, you either have to really, really know what you're doing, or you have to, for example, or you have to stick to certain shapes, or you just have to calculate that into a cost. So metal powder bed fusion is just works like it's a sintering process where powder is heated by a laser or multiple lasers, and then the object is built up. It's taken, and then it comes out of the machine, and then it usually needs to be hipped, or it used to be kind of some post-processing. Usually, compared to the other processes we've mentioned, usually this is more accurate. If you want a satellite part or an orthopedic or like implant inside the body, you would probably want to use this technology. The problem with it is because of the post-processing and the time in the machine is so expensive. So generally 3D printing is bigger, is more expensive because we have bigger machine hours. More layers is more expensive because that layer, upping up a layer takes time. And then also post-processing, like every technology, takes time. So you need to de-stress it, hip it, all that, and that's going to cost you money. This would be a really great technology if you wanted like thousands of something and you wanted to dial it in. Maybe it has some variability. Like there were some people using it for fingers, I think, at one point. And that's kind of the case. A relatively small mass parts that have to be accurate, that can be mechanical, and that maybe there's a customization element here. Because they were used to make millions of teeth parts, for example, bridges and crowns and stuff like that. And you can do that customization really well with these technologies as well. But, getting your first part, if you want to invent something, you're just going to go to these guys like, hey, make this. It's actually quite difficult because there's thermal stresses on the part, and they have to make a support structure to keep the part from ripping itself apart. And that, if they do that wrong, then it doesn't work. And then, it's quite expensive. It might take a couple of days, actually. So that's powder bed fusion is the one you're most likely to find, but it's not necessarily the easiest one to work with day to day. There's some other technologies like HeadMade uses a plastic sintering system, right? Like you could use a Sinterit or other sintering system, and then you could turn that part into a metal part using this HeadMade technology. That's also quite affordable because these desktop sintering systems are also quite affordable as well. There's also, like, if we're looking at like a powder bed fusion installation, by the way, you're talking about several $1 million if you want to do this correctly. You're talking about HVAC, you're talking about leveling your floors, one of these Linda gas containers outside for inert gas. You're talking like, and I wouldn't have one. If you could buy one of these machines and run one, I wouldn't do that because it's just not very profitable. You need several. So we're talking like a $5-6 million investment to make this work. So, for the orthopedics crowd, prosthetics crowd, like maybe one service can specialize this in America or several in a region. This is not something you would expect in every city, let's say.
With that, I know you've got multiple materials and such, and I've always heard, pretty much everybody dials in stainless, right? What is it, stainless 304 or whatever?
316. Yeah.
316, yeah.
Yeah.
So they dial that in, but then when you start getting into like the titaniums and such, which are, more difficult to print, and then more machine specific, right? So I think I guess my question to you is, if I was to have a part, I kind of have to decide which way I'm going to go, right? Whether I'm going to go binder jet, that sort of thing. And then you pretty much, that's where you stick to it, because there's going to be multiple iterations to get to your piece. It's not like, oh, hey, I proved this out in binder jet, and now I'm going to go, do something on powder bed fusion.
I think it's a really, really, really good point. There's two things at work here. That very few suppliers have all these technologies in house. So it's not like in plastics, maybe you could find a supplier that has 4 or 5 of the different printing technologies in house, and they'll just equally weigh them and be like, for this part, go with this one, right? But even then, we would probably have to design or redesign a little bit compared to the constraints per process. But I think it's a really good point you make for, there's this thing called design for additive, and everybody's always talking about it, but there is really it's really process specific. And especially if we get into metals and stuff, there's different constraints. Like wall thicknesses are completely different. Wall thicknesses can be different per material. The file could be optimized per different printers. And indeed, if you would go from one printer to the next, it doesn't even necessarily mean that it can print on the second machine. The processes all work for different part sizes, and they're all kind of optimized. So that's why I try to give a guide. Like if you're looking for stuff like between several centimeters to 20 centimeters, something like that, powder bed fusion is really great. It needs to be accurate, but it'll be expensive. DED can also do that, but not do the lower end, the several centimeters. It'll be super cheap, but it'll be literally rough. It's like metal cheese whiz, essentially. Binder Jet could do the smaller end of these parts, and they'd also be like $20, right, for smaller parts. And they could be some kind of mechanical-ish. But if you really want some kind of interlocking complex mechanism, then you probably want to go back to powder bed fusion. Now, if you need a lot of really small parts, then something like this Hollow AM, this slurry SLA, could really spit them out like super duper cheap. So that could be, that's kind of like how I would look at it. And you're right. I think the biggest problem often is that if you go to a service bureau, they only have powder bed fusion. That's what they're going to sell you. And what they really should be selling you is a journey. And it's a learning journey for you to design for this technology and to get to know it and stuff. So be upfront, talk to several service bureaus, see where it clicks. And I think it definitely in the beginning, see where you can do like a lot of development work for you, for example.
Yeah.
Right. So because you're going to have to learn, and you can't just, it's really difficult to pick up a book and then design for one of these technologies because it's all really, very, very specific.
Well, tell me about okay, so you said there is the binder, like the FDM style, and then you can send it off to be sintered or what have you, and you do that with a partner. Sounds fairly accessible. Would that be like a good starting point? So for instance, in the prosthetic realm, we have things like that connect the prosthesis to the foot. So they're called tube clamps, pylons, pyramids, that sort of thing. And machining them is very inexpensive. People machine them like crazy, but we've been using the same types of connectors for 80 years or maybe even more. So there really hasn't been a change in the way we connect the sockets to the feet. And I think there are better ways to do it. So let's say, as far as the journey, right, is a journey like, hey, maybe we get a mechanism that it thinks we're going to make it work. And so you can very inexpensively do like a multi-jet fusion part or whatever, just to prove out that the mechanism works. And then I've seen some of these, Mark Forge parts. They're beautiful, but I know that there's a lot that goes into that as well. But they've dialed a lot of that stuff in their software, right? So I'm just wondering, like, is that a reasonable journey to start? Like, you have your mechanism, and it's like, okay, then you maybe talk to a couple of bureaus that may have a couple different technologies and say, hey, this is where I want to go, and this is where I need to be price-wise. How do I do it?
Yeah. I think the first journey should be, you should go to some local machine shop with a lathe and a mill and a VMC and all this stuff and ask them if they can do it. It's always going to be simpler to machine it, right? And the machining guy should look at you and say, no, this is possible, and then you go do additive. I think in this sense, unless you need something that's ultra lightweight or ultra porous, or you want to change the modulus, right? You want to make that thing more springy, or you want to make it like less stiff or stiff in a particular direction, or you want to make like kind of like a compliant mechanism, or like kind of like a shock absorber kind of thing. There, we can do things out of that you can't normally do with these other technologies. So you can make that thing cushion more, or you could make that thing break only in one place, right? We can program the thing to have a crumple zone. Say, okay, if it breaks, it'll always break here. So the guy can kind of injure himself, but he's not going to injure himself as badly as if it breaks in the other part, that kind of stuff. So all that kind of stuff really makes sense. And then when machining stops, and then all these lighter weight, smaller parts can make sense. And you could get a service bureau that can get you a great deal on them. And I would really go to powder bed fusion service first to go low volume parts, because it's difficult, but they'll tell you straight off the bat because they want to make money on it, right? So they'll tell you straight off the bat, like, it's $300 or $3,000, right? And then you'll have your part. That's usually easier than going with the Mark Forge. Now, if you said, you know what, I'm making like some kind of robot hand, right? And I'm going to need a ton of like little parts. Okay, then for example, going the Mark Forge route, if that works, buying the whole Mark Forge setup is a week building with your metal printer, right? Not even, right? So definitely, if you're going to go that, I would buy the Mark Forge setup and experiment with that to see how many of your parts you can get, because per kilo, these are so much cheaper than the parts you're going to get from the powder bed fusion machine. But that's for somebody who's saying, like, I want to develop a device, I'm going to be making 300 of these a month, and the powder bed fusion price is too much for me. How much can I save with the Mark Forge compared to something like that, right? That's what I would. It's a very logical approach, but there's not, and it would also depend what you're going to be doing. If you're going to be doing like kind of like joints, just like our finger joints, Mark Forge is a beautiful process. But if we want something that's super porous, and really ultra lightweight with a kind of a lattice structure, then we're going to have to go to like the more powder bed fusion stuff, So, and then in the middle, we could do some kind of porous structures with binder jet, but not always, right? And this molding process, that works, but not if something interconnecting change is really difficult with that,
Right.
So
right.
it really depends on your design rules. I mean, just talk to a bunch of experts. And like also just the pricing of the service is reflective in how much work they put in and how bad that part is for the service. And always try to ask them, because sometimes it's like the wall thickness doesn't work, or we have to print it at 45 degrees, or it's just too big, to fit in, well, this is the example I always work. It doesn't really work with metal, but if I, this, Brent, but if I print a hollow giant thing in plastics, I can stuff it full of stuff, right? And then it's great. If I close that hole and make a smaller vase or whatever, all of a sudden I can't fit anything in it. So then all of a sudden this part becomes really, really expensive to do, right? And the same thing is for metal printing. It depends on the process, but it depends sometimes on how size it is. Maybe a lot of times you have to put them at 45 degrees, and all of a sudden it doesn't fit in the printer. So there's really individual process constraints, and this really bizarre thing is that also there's constraints around the pricing model. So some companies will have a pricing model on a volume. Some companies will have a pricing model that's super duper complicated. So maybe one technology may even makes more sense, but because some guy's doing crazy pricing, then maybe the other technology makes sense in that case because they're just trying to buy market share. So just shop around. But I think the things that are successful in this case is find a partner and find one that's like physically close to you or culturally close to you. You should feel very comfortable working with these people, and you should be able to communicate well with them. That I think is really important.
I think one thing that I guess resonated with me with the metal stuff, I always think about something that's rigid, right? Or a connector.
Mm-hmm.
You mentioned some dynamics, right? And, just like TPUs and such, I believe have been complete game changers for what we're doing for comfort for patients.
Mm-hmm.
I mean, it sounds as though what you're saying is that there are some opportunities for manufacturing in 3D printed metal that provides some dynamics, cushion, shock absorption, all that sort of thing, maybe some torque stuff that, that I don't know of anybody that's working on that stuff. And not that we're trying to give people business ideas, but hey, if you've got the pockets to do it, that sounds very interesting.
Yeah, I happen to be trying to work on some stuff like this and for other stuff, but so what we can do is we can dampen things, and we can do shock absorbing in certain things. And so dampening is just vibrations, and the shock absorption is just like the rock shocks kind of thing that you can do on your bicycle. And so you've probably seen one of those. And you could do mechanical versions of these, and mechanical versions of these that you print in one go. And that's very exciting. Now, of course, these devices would be very expensive because like you're talking about a mechanism that would be quite, well, for us, Coke cans are quite large, right? So you have to understand that within 3D printing, we always see things in a much smaller scale than maybe other people, like a welding guy or whatever. But I think making these kind of like really optimized parts, especially in a kind of like comfort shock absorption way, I think is really, really very exciting. It's a very exciting area, I think, to move ahead. And the other thing I think would be really exciting is just low volume parts so you can order on demand from like a local service, right? That you maybe don't have to wait for, so you don't have to wait for certain fasteners, or you don't have to wait for certain things. And the other thing is just like, once you've got a partner set up, the part from design to delivery, that time to market could be considerably faster as well. That's not going to be the case when you first go to these guys and get your first part, right?
Yeah.
But once you set up, once you have somebody or multiple someones that understand the technology, once you have a good relationship with Sarah, your metal printing guru at your client or your partner, then you can really accelerate your time to market. Now, typically, we must realize that additive parts are more expensive than conventionally machined ones. And there's certain cases where they're not. And when they really, really make sense is things that are small, few layers, or have a particular quality, property, or shape that we can't make with another technology. And from a company perspective, 3D printing will work really well if you're solving a problem, or if you can't do anything with it, there's no other solution, or it's really very, very time constrained, or the geometry is a really, really killer thing that they use. Like it has to have this porosity, or it has to be a metal mesh, or it has to be kind of a wire. And we can do TPMS structures, cellular structures. We can do lattice type structures. And these can all be like, you can actually design your own properties for a part. You could really design a material for Bulb's leg. He could have a really particular material for that application for him, just for his individual comfort. And you're right. This is very, very nascent as an area. This is very new.
Can you talk a little bit about threads? So like, do you, with these things, do you need to be able to post-process these threads? So like you're going to retap them or something. So maybe the threads are a little bit rough or something, because, a lot of our stuff is assembly sort of thing, but what would be interesting is that there are some parts that can be machined very inexpensively. And then you might want to connect it to a piece that's very, very custom, but it takes threads to make that happen. Can you speak a little bit to that?
Yeah, it's really technology dependent. And usually it's a separate process, right? So you would tap threads just like you would do it in another process, separate of the 3D printing approach, typically. Now, first thing, the one thing we can do with 3D printing that's exciting in that realm is the fact that we can design for flow, or we can design to optimize the whole object. So we can take these 15 things that are usually assembled and make it into one, right? Or we could make it to reduce the assembly time. Right, so maybe we'd end up with a more expensive part. It's $100, but instead of 2 hours of assembly, it's an hour of assembly. Now, maybe that's a big difference for us, and then we can do it. So we're more flexible in getting the geometry to fit the particular problem. So that on the advantage side. On the disadvantage side, yeah, mating surfaces are difficult. You have to machine them for us, typically. And threads, you usually would tap on there are other ways of doing it, or having the hole there already, or having some kind of prepared thing. But usually you were going to have to tap that using a conventional process anyway. And usually it's cheaper, right? So the 3D printer may cost $100, $200 an hour, right, to run. And the post-processing is going to be pretty specialized around your workshop as well. Typically it's like Bob is the 3D printer guy, and everyone can maybe take the stuff from the 3D printer, but all the other stuff is probably very localized. Whereas tapping a thread or something, or machining something, maybe like there's a half a dozen people that can do this. So, typically the machine time is going to be the real thing that really influences you. But if we can design for maintenance, right? Or if we could design for assembly or design for fitting, for example, then we can do things that other people can't. And then we maybe can reduce the part count, right? So we make 8 parts into one. Or we ultra lightweight it to make it really different, or we change the mass of this part to such a degree that I don't know. I used to be able to let's a whole separate assembly. Now we can integrate it into this. We can integrate the functionality into something else.
Yeah. So I mean, and I guess the other part that's interesting, like if you know that you're going to have to do some post processing or tapping, then you can actually use say a Mark Forged FDM machine to create your tooling to hold that for the machining process. So it's not a big deal, right?
No, it doesn't necessarily have to be. Mostly you'll charge extra. And that is one thing. It's like, I call it the gateway drug. For a lot of people, like this tooling, jigs, fixtures, all that stuff is the gateway drug. I think, and still, that's another thing we maybe want to talk about in another episode. There's a lot of end of arm tooling and jigs and poka-yoke stuff you can make with 3D printing. And that's a really nice way to get into the technology as well. Because you're not making something that will cause somebody to trip. It's something you're making to work with better. So it's a really nice way to get to grips with technologies as well. Yep. So I think maybe we should talk about that in another episode also.
Well, this was great. And I hope that our listeners get something from it. And, it also takes some of the hype away that it's very, you just don't send a file and ta-da, out it comes, and it's very inexpensive, ready to go. Metal sounds like a journey.
No, it's like one thing I forgot before I forget. There's like, for example, there's like companies, like one is LMI and the other one is One Click Metal, and they're making powder bed fusion machines at like $120K, right? So there you have a cartridge in the machine instead of like loose powder and stuff. That makes it safer, right? Oh yeah, there's also risks, right? So with the powder bed fusion, you have loose powder, titanium powder, and that wants to blow up and in a really special, wonderful way, right? Any powder is dangerous, even like at a flour mill. The powder there is dangerous. Well, it could explode. But particularly titanium powder also can catch fire and very, very spectacularly. So One Click Metal has its powder in a cartridge, which makes it accessible. Now, the printer also needs less in the way of setup and all this. And so there are people value engineering these systems for around the 120K range, where you're like thinking, okay, wait, that could make sense for a practice, right? But even with a machine like that, a Meltion machine as well is also like, I don't know, 120K or something like this as well. So that could be accessible for these rougher parts. But you need to make the calculation, how many of these am I going to do? Or how much faster is this going to make me? And definitely, a lot of people do the cost calculation, just like, oh, machine hour, this is the part, I'm going to make 20 parts. No. Are you going to have, when we see this in an industrial scale, and even like kind of like a artisan plus scale, right? How long is the machine going to print, and when is it going to be done? Right, this is the biggest problem. So if the machine has a print run of 8 hours, or the turnaround time is an extra 4 hours, who's going to do that? All right, are you going to have some dude come in at like 3 o'clock in the morning and do this? Do you have the capacity to do that? Because then, of course, all of a sudden your idea of printing like day in, day out goes out the window, right? So what you have to do is kind of print during your shift, turn around before you go home, then print overnight. And all of a sudden, whoa, you're mega utilizing your machine. And it's these kind of things that maybe make these things like all of a sudden be really cheap if you keep doing it, or the cost case of this just goes out the window because they're just running the machine 3 days a week or something, which with a polymer machine, if it makes you much faster, make sense. But typically these metal machines are going to cost you a couple $100,000 a year to just have somebody to look at, and but we are seeing with Meltion and One Click Metal, we're seeing like value engineered machines that could be in the accessibility range, but still, yeah, totally agree with you. It's a journey. It's like designing for this is a journey. Understanding it is the journey, and these machines are not closed loop, or they're not as advanced as and easy to use as all the other industrial equipment. So it's definitely a journey. We wouldn't. I'd tell everyone in this industry, get a desktop printer. Everyone. I don't care if you hate 3D printing and you think it's the worst thing in the world. You need to do that, to do yourself justice by getting just a desktop machine, playing around with it, and finding out how you can make your process better. Right, tools, little inventions you have, little unique things. I think that I can happily advise anyone. They're a couple $100 now, maybe $1,000. It's going to pay for itself, right? Now, if we want to go into like the MGF powder bed fusion stuff, I think it's like you made a decision with Advanced to be specialized in this, to really set up shop, to really understand it. Then it makes sense. But the metal printing typically is like a bet the farm type of technology. And even if a large company went in this big and did have the 5 to 10 million to do this, it could like super not work. not even like it can't work a little bit. Like it could just not work at all, or take you 24 months to get to up and running with this stuff. So it's this is something I would be more cautious, much more cautious in advising people to do this. You have to be the right people, the right amount of money, and the right business guys.
Well, and I think you hit the nail on the head. The right people, right? You can have you can spend 10 million and have the wrong people, and it's not going to work.
Yeah, and that's also a problem. There's like operator people, but also operations people in metal 3D printing are super rare. Like about 10, 15 years ago, we're selling 100 of these machines a year, and most of those are going to universities. So there's not that many people out there that can you just hire Sarah, fly her in, and she would then in Boulder, Colorado, or wherever you are, run your plant. There just aren't that many people that are experienced with this. So that's also going to slow you down. Whereas in polymer, you'll get the hang of it. I mean, there's some classes, there's some courses, lots of trial and error. But at metal printer that like fails every 2-3 days, and you're not sure where it fails and what's going on, that the learning curve is it's horrible.
Well, thanks for sharing that insight. I think I've definitely learned a lot, and I know our listeners will as well.
All right, man. Thank you. And please don't go into metal printing. That's my
you've got my word on that one. I haven't said that out.
Okay. All right, dude. All right. And this was great. I hope everybody enjoyed it. This was another episode of the Prosthetics and Orthotics podcast with Brent Wright and Joris Peels. And I hope you really enjoyed that. Have a great day.